So here is the handout related to that particular problem. This just is reiterating what the textbook did. Their assumption is incorrect. Notice from the graph, and here I go through that relationship, that here's the graph of velocity versus s. It's a linear function of displacement. But we know that v dv equals tangential acceleration ds. So dv ds equals tangential acceleration over v. Thus, tangential acceleration over v equals the slope of this function, which is 2. So therefore, the tangential acceleration is a linear function of velocity. The tangential acceleration is a linear function of velocity. So the correct approach then is to write the velocity as a function of position. So that was the linear function that you see up there, 2s plus 2. And then the time derivative of this is going to be 2s dot, but s dot is v, but v is 2s plus 2. So the tangential acceleration as a function of position then is 4s plus 4. Notice I'd made some mistakes, and you can see my corrections there. When the velocity is 3, we put a velocity value of 3 in. That means s position equals 1/2. We've had 1/2 meter of movement of the tape. The acceleration, tangential acceleration, happens to be 6 meters, and that should be seconds squared. 6 meters per second squared instead of the author's 20 meters per second squared. Okay. Hang on for a second more. Okay. Okay, now, so that ends up, did I finish their problem? I don't know. Well, anyway, that's the tangential component of acceleration that you would use. You would use the normal then, and you'd figure out the magnitude of the acceleration to answer the problem correctly. Now, here's something that's more useful or interesting. Finally, note that if the tangential acceleration is constant, then here's the behavior that would have to occur, resulting in this equation that we're very familiar with. Well, what kind of a graph is this, folks, if that at is a constant? That's a square root function. It happens to be a square root function that looks like your traditional square root function that's had some distortion applied to it and a horizontal shift. So that graph of velocity versus position would have to follow, would have to track a square root function of this behavior for the acceleration, tangential acceleration, to remain constant. And then I had at the bottom there, I had some additional information that I don't think I need to talk about right now. This is essentially what I talked about a little earlier out of the book, right here. And then here is that same concept. You can look right down here, since that velocity, I will talk about it, since that velocity as a function of position was linear, then you can look right here, if I use equal scaling on it, and I can look right here and see that the tangential acceleration grows from this little small value right there to a larger value at 3 meters per second velocity. And when you're at 18 meters per second and your position is 8 meters of tape, you got a much greater value of tangential acceleration. Yeah, Alfred?
Where exactly does it say that v is linear to s? It just says it increases uniformly while 8 meters of tape passes, but it doesn't say if that's uniform to the space or the time.
Right. I agree.
Okay.
And so,
Right.
yes.
Because I was going to say that if you went a different approach, you didn't even involve the equation v dv equals ads. you have to admit, if you start at 2 meters per second and go to 16 meters per second, there is some linear acceleration that would result in that resulting distance being 8 meters that you traveled, right? I mean, there's got to be some acceleration that's linear.
There could be.
Constant.
There could be a constant tangential acceleration value.
That would result in that 2 meters per second to 16 meters per second covering 8 meters.
Right.
And see, that's the thing is I did that calculation. I said the area underneath this increase in velocity, solve for the time it would take to get an area underneath that curve to be
good.
And that would result in the same 20 meters per second that they got.
Oh, you did get that?
I did get 20. So the question is, what is the wording really of the question?
Yeah, so I think it comes down to the interpretation of the wording. And
right.
The point you made, Alfred, is valid. So is yours, Ian. And I think what I was conjecturing might be valid as well. So it was an oddly worded question. Yeah, it's poorly worded, I think. So anyway, yeah. I think it's a useful thing for you to be aware of, though, and something that might have slipped by you earlier in the course if I had brought up that particular function, v as a function of s, and discussed it at that point in time. But I think now with the experience you folks have had, that probably makes this discussion probably makes a lot more sense to you. Okay. Let's see if anybody has any questions about any of the material. Yeah, it's kind of broad. Oh, you might want to know what's on the final.
Yeah, that'd be nice.
Right? Okay. So I would suggest, well, I'll let you suggest. What do you think? What do you think you could expect for a final exam in this course, based on?
Just pulleys.
Oh, now that can get interesting, though. Just pulleys.
And observation.
Okay, so the fundamentals that we covered in the course were particle kinematics, which means that you want to be very comfortable with dv dt equals a as a scalar equation. If that's a scalar equation, then v here is what, physically, for the particle? The speed, isn't it? And so that means this is tangential, okay? That means that's tangential, okay, even if it's on a curved path, okay? And then also, of course, ds dt being equal to v, and v dv, then once you eliminate, as we've said before, the time parameter, you end up with this differential equation, okay? So particle kinematics, pretty important stuff, and those problems can be pretty interesting. Then we start moving into curvilinear motion instead of this rectilinear kind of an approach. And so we have curvilinear kinematics, again applied to a particle. And we used both rectangular, polar, and a third, normal tangential. Particle motion, curvilinear motion. The rectangular approach lends itself nicely to motion like projectiles, etc. You're pretty comfortable with that. Okay. Polar, things that operate nicely or relate nicely to some kind of a pole. Some kind of a pole, oftentimes. But general motion actually is pretty nicely described this way as well. And then if you're only concerned with velocity and accelerations, then the normal tangential is path independent. Remember that. Path independent. Okay. Once we covered those, I think we did a little bit of stuff with space curvilinear motion as well. 3D, just touched on 3D. But the vector mathematics you've been learning covers all that. So you can just rely on the more recent vector mathematics, and you can do n-dimensional types of work if you wish. We will not cover that on the final. Then I believe we had some constrained motion, where we might have more than one particle. Now let's see, is that moving into kinetics, or was that still?
That was the tail end of kinematics.
I think so. Yeah, I think so. Yeah. So we had some constrained motion there. And that's pretty nice and the nice way when we're dealing with pulleys and multiple objects, multiple particles. Oftentimes writing an equation for like the length of cord was useful. But if you have a pulley system with multiple pulleys, sometimes using differential rotations in your pulleys is a useful way to go on working those out. That would be a pretty good item as a potential exam question. Obviously, something up in here, probably with all three of those coordinate systems would be appropriate. And then, of course, something back over here as well on the rectilinear motion. Then we started moving into particle kinetics. And this most recently on your midterm, we had some stuff here with F equals ma. And then we did quite a bit of stuff in curvilinear motion there. And then we treated acceleration as dv dt and did what then with it? How did we transform F equals ma? We then kicked dt over with the forces, and we created our impulse momentum concept. Okay? Actually, and before we did that, after F equals ma, before we did impulse momentum here, linear impulse momentum, is we actually went ahead and worked up a line integral by let's see, we developed this, and that was equal to the change in our kinetic energy. And I didn't spend time on it in this course, but a line integral like this oftentimes is usually path dependent. But for the particular kinds of force fields we were dealing with gravitational force fields, central force fields, and for elastic potential or elastic energy, or the work done due to springs, is this becomes independent of the path, which was pretty nice for us, because then we were able to go ahead and just come up with this being path independent, being equal to the change in kinetic energy, which you're pretty familiar with. And we then broke this up. We restricted what we called the work done to certain types of things, and then over here, we created our potential functions for gravitational potential, change in gravitational potential, and change in elastic potential. And the sum of those we called the change in the dynamical energy in the system is equal to the work. And frequently we have conservation of dynamical energy, meaning that there's no other work done. So this was then 0. One of your exam questions had that last exam question. Particle, a spring loaded, getting shot on to a quarter circular arc, comes on down, and at a certain point, based upon spring stiffness, amount of compression in the spring, and the mass, and the radius, that thing would leave the surface and become a projectile at a certain angle. And so you were able to use conservation of dynamical energy, delta E equals 0, to work on solving that. Okay. The other concept was to, let me go to the next board, is we had angular impulse defined, remember, as R cross mv. And we worked up the fact that the applied torque on a system acting over time is equal to the change in angular momentum in the system. Okay. That concluded the particle kinetics, and then we went back to kinematics, but this time with rigid bodies. Rigid body kinematics. And that's where we ended the course. Okay. And that's the more recent material where we started with a position vector is equal to another position vector plus a relative position vector, and then differentiated those. Okay. Usually in a course like this, matter of fact, if you take the same course at Oregon State, I think they teach it as a 3-credit course. I think they zoom through a lot of this stuff much quicker than we have here. And they go on into rigid body kinetics, which you've had some exposure to in physics. Like a bar, say a bar of a certain length, and it might be in rotation. And there's some inertial resistance to that as it rotates. And so you have to account for that as you do the kinetics, as the rigid body kinetics. But over the years, I've always thought that if I give you folks a really solid grounding in the kinematics, that you're going to be able to pick up the kinetics pretty easily on those rigid bodies. I've said it before, I'm always frustrated with this course because we have such a limited amount of time. And here we are, 10 weeks, and we're done. And the reality is we could spend another 10 weeks easily just in this same book and still really challenge you folks with a lot of interesting stuff. So that pretty well ends the course. I would suggest you hang on to this book because you're used to the layout of it, and you can use some of the material that's in these sections we haven't covered. You can use that as reference, good reference material for you in some of your upper division courses. Okay. So I think what we'll do is we'll end the recording, and then I'll go ahead and pass your exams back to you, and we'll sort of see what you want to say about the essays and what you got from the reading. So.